So in this video, what I'm going to do is review a little bit about what we did yesterday with compound interest real quickly, and then I'm going to take you through the rest of the notes so that you have those and are able to work with the number E. So yesterday we compounded interest using the compound interest formula, which is right here. You should have written down what all of the different letters stand for. And what I did was I changed the N value in class. And we let Desmos do all the calculations. And what we found out is even if you compound as many times as you possibly can, this number maxes out. Now, it doesn't max out like to an exact number. The decimals keep, raising a little bit, but they're going to raise all the way out here. So when I say it maxes out, it actually approaches a horizontal asymptote. And that horizontal asymptote is that number that you're seeing, 2.718281828. It keeps going on and on. It doesn't repeat like that forever. That just so happens right in, at the beginning of the number like that. But that number is actually the number E. So it's a lot like pi insofar as that it was given a letter. Pi was just given a Greek letter. And it's also irrational, which means it does not repeat and it goes on forever. And you can't write it as a fraction. So E, so this is E. So E is approximately, and I'll just give you the first, so many decimals. You should just know it's 2.718. A lot of teachers will say that it's like 2.72. So I think what we'll use in our class is we'll use 2.72 for E. So you should know that E is approximately 2.72, but it kind of looks like this for a while. So it goes 2.7, it's a decimal, sorry, 2.718281828. So it repeats right there and then it stops doing that. And then the next is like a 45, 45, 90 triangle. So it's kind of easy to remember. So it goes 45, 90, 45, and then I run out of memorization. So it's an irrational number. It goes on forever. There's no constant repetition or anything like that. E was actually first discovered, like we said yesterday, by the Swiss mathematician Jacob Bernoulli. I'm spelling it wrong. Noulli. There's a short video on Canvas that tells you a little bit about Jacob Bernoulli. So if you want to give that a quick watch, it's about 2 or 3 minutes, so it's very short. It tells you about one of his students named Leonard, and this is going to look like Euler, but it's actually, it's going to look like Euler, but it's actually pronounced Euler. So one of his students, his name, he was also a Swiss mathematician, his name was Leonard, and then the last name looks like Euler, but it's pronounced Euler. So Euler. He actually took some of Bernoulli's work with compound interest, and he's the one that actually named E. So Bernoulli discovered it doing compound interest, and then Leonard Euler was actually the one that gave it the letter. So here's how you use E. We compounded all the way up to every second, but Bernoulli and Euler thought that that wasn't enough, and so what they wanted to do was they wanted to compound continuously. So they have a formula for that, and I call it the PERT formula because the letters literally spell PERT. So so what we did when we compound any amount except continuously, and continuously you realize has to be like theoretical, right? Like if I ask you how often continuously was, you couldn't tap that out or snap out that time. But if I ask you to tap every second or every minute or every hour, you could do that, right? Because we have clocks that take care of that. So if I want to compound any amount except continuously, I use the formula from the first page, A equals P 1 plus R over N to the NT. But if you want to compound what's called continuously, here's the formula that you use. It's A, so that's the ending amount, equals P, that's your initial amount. Now instead of the 1 plus R over N part, we use the letter E, and that's 2.71828, etc. There's an E button on your calculator. If you type E into Desmos, it knows what you mean. And then we're going to raise that to the R, which again is the interest rate as a decimal, times T. Okay, so R again is the interest rate as a decimal, and then T is time. So how long you leave the investment in there. Okay. So if we want to compound continuously, you'll see that in the problem. You'll just use E instead of the 1 plus R over N. E has another definition. So what I want to show you is if I graph, so let me pull up Desmos. If I graph that 1 plus 1 over N, well, we have to use X, sorry, X to the X. If you look at that, we're going to ignore that for negative numbers. We're just going to look on the positive side over here. And if I kind of zoom out, I want you to keep an eye on what this graph is doing right here. It actually has a horizontal asymptote, okay? And its horizontal asymptote is actually at E. So we would say, let me just give you a horizontal asymptote at E. I'll dash that for you and show you that this graph is just going to keep approaching that horizontal asymptote. Now it looks like it kind of touches it, but I promise you it doesn't. But so what we could say is, and I'll do this as like arrow notation first, we could say for f of x equals the graph of 1 plus 1 over x to the x. Now where am I getting that? Well, that's from right here. Right? Bernoulli said put $1 in, so there's an imaginary 1 here. Do 100% interest, so that's the 1 that's here. I have to use x's because of Desmos, but these x's really stand for the number of times you compound. And then t, let's leave it in for a year, that's equal to 1, right? So there's 1s all over the place. Well, even if you let x get infinitely large, so as x goes to infinity, so let me show you here. So as x goes to infinity, right, I compound more and more and more often. My graph, which I called f of x, so I won't use y here, f of x approaches E. So not infinity or anything like that. It approaches a horizontal asymptote of E. So in calculus, we learn what's called a limit. And so instead of writing it in what's called arrow notation, we actually say the limit as x approaches infinity of 1 plus 1 over x to the x is equal to E. So this is the actual technical definition of what E is. It's the horizontal asymptote of this function right here. And then in calculus, you say, well, that's the limit as x goes to infinity of this function. And this function came from right here. So compound interest created this. And then when you graph it, you can see that there's a horizontal asymptote right at E. So that's what E is. All right, so I'll show you how to work with some of this stuff, and you're going to need a calculator or Desmos. It's up to you, whatever you want to use. Here's the graph of y equals e to the x. So it's basically, not basically, it's pretty much this. Y equals 2.71828 forever, all to the x. So it's just an exponential function. It's just the base is e. It has the horizontal asymptote that you're used to. It goes through 0, 1, and then its second point is 1e, right? 1 and then the base. So it looks exactly like the exponential growth functions that we've been dealing with. Okay, so let's do some compound and simple interest. So, let's do compound interest. We're going to compound 2 different ways. So first, we're going to compound monthly, and I'll write that in blue. And then the next thing we're going to do is we're going to compound continuously. So it's 2 different formulas, and I'll do that in red. All right, so the compound monthly, right? So here's monthly. A equals P times 1 plus R over N to the NT, where N, if we're compounding monthly, is 12, because there's 12 months in a year. All right, so let's figure out what we have. A equals, so we're putting in $8,000. 1 plus, the interest rate is 7% for this one, so that's 0.07. We're compounding monthly, so N is 12. Again, N is 12 up here. And then we're leaving the investment in for 6 years. So I'll underline, let's see, the only thing that's different between the two is how often you compound, and then the interest rate's also different. So make sure you see that. At this point, you'd type this into your calculator, or you'd go right to Desmos. So I'll do it in Desmos so you can see it. So in Desmos, that would be, let's see, 8,000 times 1 plus 0.07 divided by 12 to the 12 times 6. And that gives us $12,160.84. So that would be the amount if you followed those investing rules. So 160.84. Now let's use the different formula for compounding continuously. So for continuously, it's a different formula. Principal, E, rate, time. So this one actually pays 6.85%. So A equals same $8,000. This part of the equation, though, isn't there, right? It's E instead. So E, the rate is 0.0685, and then the amount of time we're leaving it in there hasn't changed, so it's 6. When you go from a percent to a decimal, you move the decimal place to the left twice. So 6.85%. If you want to get a decimal from that, you go 1, 2, right? Okay, so let's go to Desmos and type this in. On your calculator, you should literally see a button that says E, and that's what you're going to use. So this one would be 8,000 E. Literally, I pressed E on the keyboard for Desmos to the, and then it's going to be 0.0685 times 6. Whoops. And that's going to give us $12,066.60. So we left it in there the same amount of time. We compounded more when we compounded continuously, but the interest rate was lower, so that's why we ended up with less money. So this is $12,066.60. So there's the two different investments. All you have to do is remember, when you compound anything but continuously, you use this formula. And when you compound continuously, you use this formula.